So we just did an example in another video of probability distributions, and those are fine, but normally we have to do them by doing experimental probabilities or having an example where you can actually calculate them by using sample spaces. But that doesn't always work for every situation. There are some situations where you have certain experiments, you can actually calculate probabilities for you without doing the actual experiment. And that experiment we're going to talk about, there's lots of them, but the one we're going to talk about today is what's called the binomial probability distribution. And so this probability distribution, the binomial, comes about because you have a binomial experiment. So what you need to look at is you need to decide, do you actually have the properties of a binomial experiment? So let's talk about what those properties are, because you have to make sure these properties are met before you actually can decide you can use the calculations to get the probabilities. And the first property that exists is that you have a fixed number of trials. A trial is how often you repeat the experiment. So if you repeat the experiment 10 times, then that would be your number of trials. So it's each time you repeat the experiment. So let's say you're flipping a coin, you flip that coin 100 times, then you'd have 100 trials. Reason we say a fixed number is you don't just say, I'm going to flip the coin till I get a head, because that's not a fixed number of trials. You actually have to say, I'm going to flip the coin 20 times and count how many heads I get. So that's your first property. Your second property is that there are only two outcomes. And we call those outcomes success and failure. But I want to point out that success isn't always a good thing. It doesn't mean that this is a positive thing to have happen. It's that you got what you were looking for. That's what a success is. You actually found what you were looking for. So you might be actually looking for flipping a coin and finding out how many heads you get. So therefore success would be getting a head. Or it could be that you're looking at your items that you're creating and you're looking for how many defective items you have. Your success would be finding a defective item. That's not a good thing to find defective items, but that's what you consider a success in this experiment. A failure is not getting what you wanted. The next, and these are not necessarily in any special order, but usually we do the fixed number of trials first and then go from there. But the next one that we have is that the trials are independent. And what we mean by that is that one trial does not affect the next trial. So in other words, if you flip a coin 100 times, it doesn't remember what it did the time before. So each trial on that, each flip of the coin is independent of the next flip of the coin. Each item you check on your assembly line, hopefully they're independent. Hopefully what happens to one isn't being affected by the rest. But it could be, if you think about if you're manufacturing something, if one of your equipment has gone bad, then they aren't going to be independent. But in a lot of cases, we kind of think of them as being independent, and we work with that idea that they are in fact independent, and they're not going to change the probability of the next event happening, or the next trial happening. And then the last one is that the probability of a success is the same for trial and trial, from trial to trial. In other words, you'd have the exact same probability of getting your success. You have the same probability of flipping a coin and getting a head each time. It wouldn't change just because you did something different. You have the same probability of getting a defective item from one item to the next. Again, that one can be a little iffy because if your equipment's going bad, then there's a problem. But that's why we do these. We assume there's not bad, and then if we see things happening, we know something must be wrong. So that's why we do probabilities, is so we can see what is wrong and what's happening in these. And so if you're looking at guessing on a multiple choice test and your trials are going to be independent and you want those probabilities of success being the same from trial to trial, it means that each question has to have the same number of responses. So you can't have question 1 have 5 responses and question 2 only have 4, because then your probability of guessing the right answer would have changed. So this is just one of the other properties. So for all 4 of these properties must be true. If all 4 of them are true, then you have a binomial experiment. And that means we can actually calculate using the binomial formula. And that binomial formula, I'm going to write it down. We will never use it. It's really a difficult formula to work with, so we won't ever use it. But I wanted to write it down so you can see what the formula looks like. And what the formula looks like is the probability of getting so many successes. So X is usually what we write for successes, and we want to say that equals R. And that's going to equal the number of combinations of N choose R, P to the R, and Q to the N minus R. So before you freak out, let's explain what all these things are. So the first one is that X is what we write down for the number of successes. That's actually your random variable. That's actually what you want to write down as your variable that you're measuring. So each time you do some item, you figure out, do I have defective? Do I not have defective? And you look at all these things, and then you count how many defectives do I have, or how many heads do I have, and that's what X represents. Little r actually represents how many successes you want to find. So it actually would be, little r would actually be the number of successes you want. Oops. The number of successes you want. So if I want to see if I get 10 heads, then my r would be 10. So it's how many successes you actually want to observe. P is your probability of success. And again, the success is not necessarily a good thing always. If you're looking for the number of defective items, then your P would not be, would be whatever that probability of success would be. But again, success is not necessarily a positive thing in this case. Q is the probability of failure. And again, success just means you got what you wanted. Failure means you didn't get what you wanted. Because these are complements of each other, either you get a success or you get a failure, then Q is always equal to 1 minus P. And then this C and R thing, this is actually N factorial over R factorial times N minus R factorial. And what this factorial means is N factorial means you're going to start with N, you're going to multiply by the next number down, N minus 1. You're going to keep multiplying by the next number down till you get down to 2 times 1. So as an example, 5 factorial is 5 times 4 times 3 times 2 times 1. Your calculator will do this for you. It will even do this combination for you, but we're not even going to do any of it. We're going to use R to figure out all of this. And the reason we want to do that is this formula is not that much fun, but this is also just the probability of it actually equaling a value. A lot of times we want to look at the probability of X being greater than a value, or less than a value, or less than or equal to. And if you do greater than or equal to, it means you have to start at the R value and then keep adding all these values up each time until you get up to however many items you have. Oh, and I forgot to mention one other thing. What is N? N is your number of trials. So it's how often you completing the experiment. So if you're going from R, if you're saying X is greater than or equal to R, then you have to go from R all the way up to N and calculate that formula every single time. And that's not a lot of fun. So we're actually going to use RStudio. And what we do for RStudio is the formula is, the process is, I should say, the command is, if you've been looking for the probability of X equaling some value R, then that is actually equal to the binom, the binom. And then you're going to put in your R value, whatever R value you had there, your N value, however many trials you have, and your P value, your probability of success. If you want to do probability of greater than or equal to, you don't have to actually do each one of these. You just actually can do, actually we'll do less than or equal to first. That is actually a different command. It is actually P binom. And again, you put in your R value, your N value, and your P value. Now we don't always just want equal to or less than or equal to. Sometimes we want greater than or equal to. So X would be greater than or equal to R. And this would be P binom. But then things get a little weird. I'm going to write down that it's R minus 1, then N, then P, and I'm going to explain why it's at R minus 1. So let's, as an example, let's say N equals 5. And I want to know the probability that X is greater than or equal to 3. Well, if N equals 5, then R can be the numbers 0, 1, 2, 3, 4, and 5. So if we're looking for the probability that X is greater than or equal to 3, then we're looking for these numbers right here, that greater than or equal to 3, 3, 4, and 5, because they're greater than or equal to 3. But if I were to just do the probability that X is greater than or equal to R and not do the rest of this, and I've left off a command, I got to put that in there. So sorry, I apologize. Let me go fix that. I forgot to do something very important. At the end of the NPR, you then put in a lower tail, lower dot tail equals true. Notice the true is all capital letters. And what this is saying is we want X being less than is a lower thing. So the lower tail is true because we're down less than. And so it's going to be doing, if we do less than or equal to 3, it'd be 0, 1, 2, and 3. If we did the other way around, this would be lower dot tail equals, well, it's false because it's just greater than or equal to. So it's upper, it's up here, it's not less than. So it's the upper tail. So we say lower tail is false. So if we're doing greater than or equal to 3, then we want all of these. But R actually says, well, if you can do lower tail is false, it actually is not going to include the 3. So when it does this, it actually says, oh, you want lower tail is false, so we're just going to do 4 and 5. So if you say less than or equal to 3, then you actually get the 3, 4, 5. So that's why we do it. So anytime you see the false, just make sure you remember you have to subtract the R minus 1. Just subtract 1 from your R value. All right, so let's go ahead and do some examples of this. So let's say we have an example where, according to an article in the American Heart Association's publication called Circulation, 24% of patients who have been hospitalized for an acute myocardial infarction did not fill the cardiac medication by the 7th day of being discharged. Suppose there are 12 people who have been hospitalized for an acute myocardial infarction. So one of the things to remember about these is that we actually are going to collect, we'd have a data set which has this information. Each row in that data set would be each person, and each row would be that person, and we would have filled medication, did not fill medication. So we'd have so fill medication, we'd have a yes or a no. And we'd have this for 12 people. And then we'd count how many yeses we had or how many no's we had, depending on which one we wanted. In this case, we are looking for in this case, we're saying that our success is actually that they did not fill the medication within 7 days. So X would actually equal the number of acute myocardial infarction patients who did not fill their medication by the 7th day. All right, so we've got that. That's what our variable is. That's what our variable is, because we're going to count all of those yeses. I'm going to move this down a little bit. Okay. I'm having issues. Don't like when I have issues. We'll do this. Okay, so sorry, my computer program is having some issues. So let's see if I can, oh, there we go. Okay, now I can get it there. Okay. One of the things we need to do first is spell patience, right? Oh, man. The next thing we need to do is we need to argue that this really is a binomial experiment. So remember, there are 4 properties of a binomial experiment. The first property is that we had a fixed number of trials. There were 12 people in the study, so there are a fixed number of trials. And when we try to argue that it is, we're not just trying, we don't just reiterate these things, you actually argue and show that it is true. So there are 12 people, so there's a fixed number of trials. The second one is that there are only 2 outcomes. And in this case, they either filled the medication or they did not fill the medication. So there are 2 outcomes. Either they did not fill the medication or they did. The third one is that the trials are independent. And we can actually say that that's probably true because unless these people are all in the exact same family, what happens with one patient shouldn't affect the next patient because they're not usually in the same room together, they're not usually doing things together and aren't talking, interacting. And so the trials are probably most likely independent because what happens with one patient isn't going to affect probably the next patient doing it. So the trials are independent since the patients wouldn't affect another patient. And then there's one more, and the last one is the probability of a success is the same for trial and trial, from trial to trial. And it is 24%. And we know that because it says up here in the problem that 24% of the patients did not do this. So that's my percentage, that's my probability. So that's where I come from, and that's where that value comes from. So we do know that it is 24%, and it is the same for every trial because we do assume, again, the trials are dependent and there's only 2 outcomes and they're identical trials. All right, so now that we've done that, let's go ahead and do some probabilities. We'd like to find the probability that all filled their cardiac medication. So if all filled their cardiac medication and yet our random variable is that that the person did not, then all filled means, first off, let's write this as a probability statement. Probability is a P. Now you should do a parenthesis to say P of something. And we're saying the number of people who did not fill their medication. Well, if all did fill it, then the number who did not fill it would be 0. All right, and so then this is D binom. And then we put in my R value, my N value, which was 12, and my P value, which is 0.24. So sometimes it helps to go ahead and write that information down and actually say, hey, those are what those values are. N equals 12, P equals 0.24. So this is the calculation I'm going to do. And let's have R go do it for us. So we're actually going to go into R. And we're going to have R do the calculations for us. And then we'll show you what actually happens. So I'm going into my R program. I'm here in the console. You can actually do this in an RMD file, or you can do this in a console. It doesn't matter. And And then all you do is you do D binom. And when you start writing that, it says, hey, this is the order you're supposed to do things. So X is your X variable, or your R variable in this case. That was 0. Your size is 12. That's your sample size. And your probability was 0.24. So if you forget what order you put them in, it always comes up and kind of shows you. And there's your probability. So I can actually just copy this if I want to. If you're doing an RMD file, you don't need to. If you're doing it in a Word file, you would need to do this. Copy it and then just paste it into your file where you are. So there we are. And there's my probability. So here's the probability that X equals 0. It's equal to 0.037. So 0.037 is a fairly small number. So it'd be kind of unusual that none of them did it, but not too unusual. The next one says the probability that 7 did not. So now X again is the number who did not, and we want to know if the did not was 7. So again, I'm going to go and go back to RStudio. The nice thing about RStudio is I can actually just hit the up arrow. It'll bring back what I already typed in, and I can just arrow over and then change that 0 to a 7. I don't have to remember how to type everything in. If you do an RMD file, then you'd have to remember to type it in, or you can copy and paste, either way. So we'll now go back over here. There's our value, there's what we typed in, and here's my answer. Again, fairly unusual to have that happen. All right, so now none filled their cardiac medication. So if none filled their cardiac medication, then we're looking for the probability that if none filled it, and X is the number who didn't fill it, then all 12 of them did not fill it. So we're looking for the probability that X equals 12. So again, we're going to go back to here. We'll bring the up arrow over, change that 7 to a 12. The other numbers don't change because we haven't changed any of those. And then we're going to see what that number is. All right, so that is this number. And now you're wondering what in the world is E sitting in this number? Well, this is the way your computer and your calculators and a lot of other, mostly technology of some kind, puts in scientific notation. It doesn't know how to write scientific notation. So this is how it writes its scientific notation. It can't write times 10 to a power because it doesn't know what to do with it. So that's what that E represents. You know scientific notation. So you can actually write this as 3.65 times 10. And then somewhere on your program, you have a way to put in a superscript. And so type in a superscript, and there you've got your answer in scientific notation. Do not leave it with just the E there. Please put it in scientific notation because you know what that is and know how to write that. And you have that ability. All right, so now let's do another problem. This one says at most 2 did not fill their cardiac medication. At most 2. So at most means that many or less, because that's the most you're going to get. So X is less than or equal to 2. So the way I think of this is that most is, if I'm going to make at most $50,000, that's the most I'm going to make, and I can make less than that. So that's kind of the way I think of it is, it's going to be less than or equal to. And so now, because it's a less than or equal to, we don't use the D binom, we use the P binom. So going back to my RStudio, we're going to use P binom. We're going to put in 2 because that's my R value. I'm going to put in my 12 because that's my 12. I'm going to put in the 0.24, that's my probability. And it even does tell you lower.tail equals true or false. We want the one to be true. Okay? Because we are again saying we're less than, so we're less than, we're on this side, we're on the lower part of numbers. And then just hit enter, and there's your value. Again, I'm going to copy this, paste it into where I'm working, and there's my probability. So the probability that at most 2 did not is 0.42 or 42%. So it's a pretty good chance that at most 2 did not do it. So now the next question is at least 3. So at least 3 means, that's the smallest you're going to be. You could be more. So that means x is greater than or equal to 3. And though again, the way I like to think of it is that you're going to make at least $50,000 when you get to college. That's the minimum you're going to make, and you could make more than that. All right, so going back to our studio, again, we're going to do a p binom. 3, I'm going to come back to that in just a second, 0.24, and then lower dot tail. But because we're saying we're greater than or equal to is stuff to the upper part, stuff on the upper end. We're not on the lower tail anymore. So our lower tail is actually false because we want to be greater than. We want to be in the upper part. We're not in the lower part, we're in the upper part. So that means lower tail is false, which means that now if I did this, it would actually not count from 3 on up to 12. It's going to count from 4 on up to 12. That's how R does that. So we need to actually subtract 1 from the 3 so it'll start at the 2. So to start and get from 3 on up. So you just have to do that calculation, and then we find out that answer. And so this is equal to that value. So 57% of at least 3 did not fill it. The probability is pretty good that at least 3 did not do that. Let's do one more of these. Let's do at least 10. So this would be the probability that x is greater than or equal to 10. So same kind of idea where at least is greater than or equal to. So we're going to go at least for greater than or equal to. So p binom, and you could use the up arrow on this too, by the way, I just didn't. 10 was our value, and then 12 is my n value, 0.24 is my probability, and lower dot tail equals, again, we're saying we're greater than. So down here is lower numbers. We're up here in the upper numbers. We're in the upper value. So this would be lower tail is false because you're in the upper values. And anytime you put that false, you need to go back and change that to 10 minus 1, your R value minus 1. So that you count the 10. Otherwise, it's going to count from 11 on up. And you want it to count from 10 on up. So you just do that minus 1 to make sure it does that. You don't have to go to the end. You can just hit enter right there, and you get that value. So again, this is scientific notation. So go ahead and write it in scientific notation. 2.56 times 10. Again, you've got a way to do superscripts in your programs. If you're in Word, there's a superscript right there. If you're in Google Docs, there's a superscript also. And we want to do minus 5. Now, that's a pretty small number. 2.56 times 10 to the negative 5 means you're going to move that decimal place to the left 5 places. So you're going to have 0.00002. That's a really small number. That's definitely less than 5%. So now the last question I'm going to ask you, and this is why we do these probability calculations, we can ask these type of questions. Suppose of the next 12 patients discharged, 10 did not fill their cardiac medication. Would this be unusual? And what does this tell you? So we know that probability already because we calculated here. At least 10, the probability was really, really small, 2.56 times 10 to the negative 5th. So we know that the probability of x being greater than or equal to 10 is 2.56 times 10 to the negative 5. Again, a really small number. So this is definitely less than. That's definitely, whoops, can't seem to get out of being there. So let's see if I can do it this way. Okay, is less than 0.05, less than 5%. Definitely less than 5%. So this means it is unusual. Remember, I'm not just looking at x equaling 10. I don't want to go calculate for just x equaling 10, even though I want to know is the next 10. I actually want to look at 10 or more, or 10 or less. we're going to do 10 or more, and that is definitely less than 5%. So when we're looking at these unusual things, it's not just equal in the value, it's always a range. So I always want to look at a range to do an unusual. But this is definitely unusual. And so what does that tell me? So what it says to me, and it could be just an unusual bunch of patients. There could have been something weird about these patients that they just didn't do it. And that's always a possibility, is you just have a weird set of sample. Or it could be something's weird, something's wrong with the way you're getting people out of the hospital. So you might need more education to help these people see what's going on and see the importance of getting their medication filled. So what I would say is this tells me that we may need more education to tell patients the importance of filling the medication. Because something's going on. This shouldn't have happened, but it did. So since it did happen, something weird is happening. We need to check into it and find out why that is. And this is why we do calculations of probability, is to see, is something unusual? And if it is unusual and it happens, then that tells you there's something weird going on. Either it's just a weird sample, or you need to change things or look at things to see what's going on. And that's it.